No, so basically what I want to do is get up here and say something about how mathematics can be involved in this, what role I see mathematics, what role I see mathematicians at MSU currently playing, and where we want to go with this. Okay. You know, obviously, right now this is a field of applied science, which parts of that don't naturally mesh with mathematics, but other parts of this field really do mesh with mathematics, and it has a long history. It's actually a remarkably mathematical field when you look at the methods that have been used by people both in physics and in math, and some of the big names in the field are actually mathematicians. So on this first slide, I just wanted to mention that there's sort of a number of ways that you can look at quantum information science depending on what you want to emphasize, right? If it's, you know, if I emphasize information, then it's some sort of extension of classical information theory where we bring into quantum effects. If I emphasize the quantum, then it has to do with fundamental physics. And then, well, if I emphasize the algorithm development, which is sort of a subset of the first one, then that's another set of problems. And these are all really, distinct perspectives on the problem. But of course, and there's a deliberate joke here, that these are entangled with each other. And the development of them has come together. And they're also really, from their beginning, even before the quantum side, entangled with mathematics, probability theory. Quantum mechanics, after all, is essentially linear algebra, right? I mean, of a particular, very particular kind, or at least functional analysis, which is infinite dimensional linear algebra, although really you can do it in finite dimensions. And computational complexity with algorithm development. So here are some of the sort of key current directions where people within mathematics or theoretical physics who are particularly mathematically minded are looking at things. Quantum algorithm development is obviously a big thing. It's sort of what launched interest in the field back in the 90s with the Shor algorithm. And so one thing one's interested in is finding algorithms that beat some sort of classical complexity limits. You know, if it's exponential time classically, but polynomial time quantum, then that's really interesting, provided somebody someday builds a scalable computer. Fortunately, the mathematicians don't have to worry about trying to build those scalable computers. We just have to think about what to do with them once they're here. There is some interest in quantum machine learning. I'm not entirely sure what that is, because machine learning is itself a very practical field right now, and clearly quantum machine learning is less. But people are busily thinking about how to implement machine learning in a quantum situation, and this goes back to something that was on Phil's first slide, which is developing algorithms for noisy quantum analog computers. And I suspect, as a number of people have echoed, that some hybrid between classical and quantum is where things are going to have to go for a while, or perhaps forever, as particularly in a noisy situation. So another thing that mathematics has really played a role in, or at least mathematical methods, is sort of theorems that tell you what the theoretical limits about the field are. So, and I sort of broke these into go theorems and no-go theorems. So the go theorem is a useful example, and the one I put up here, I didn't state it, but Kitaev's toric code showed that error correcting within topological quantum community is a theoretical possibility. Of course, the toric code is nowhere near something really implementable. It's very far from reality, but it shows that in principle, this technique could work, modulo some engineering. Okay, and then there are also no-go theorems. So there are a lot of ideas that circulate around in theory about this is more of a good counterexample than an example. So for a long time, so one thing that people are interested in within quantum information science, and I think we should distinguish quantum information science, which is broader from quantum computing. So quantum information science is sort of about entanglement in general, and it could deal with communication. And one thing that people are interested in is the concept of entanglement entropy, and for a long time there was a general feeling that, okay, in a gap system, entanglement entropy satisfies an area law. In a non-gap system, probably there are just logarithmic violations of the area law, sort of taking cues from critical phenomena. And actually there were some very surprising results by Peter Shor and his student at the time, who's now at IBM in their quantum computing group, Ramesh Movasov, where they demonstrated power law violations of the area law for entanglement entropy. And these were mathematical results because they had a simple example of a quantum system for which they could prove the power law, that the entanglement entropy scaled as a power law of the system size. Okay, so those are useful things because they establish the limits, right? You have a theorem which says you can do this, or you have a theorem which says actually this idea, maybe the logarithmic violation of the area law is more or less the right idea, but okay, there's some fine print that you could better work out because within the whole scheme of things that are possible, it's not the old truth. Another area which overlaps somewhat with what a large number of people at MSU are doing, although actually I'm not going to talk about their work very much, is the structure of topological quantum field theories, which is an amazingly intense, sort of very mathematical area. It involves braided tensor categories, which I don't know what they are actually, but my colleagues do. We have a very strong geometry topology group here, very interested in low-dimensional topology. And of course, if topological quantum computing ever gets off the ground, it's going to use the structure of how it's supposed to work is lurking inside those mathematical structures. And then another area which is has a long history within mathematical physics is the statistical mechanics of spin systems. This is where a lot of the sort of cartoonish models of quantum computing are formulated. And I just mentioned a few things here: topological phases of matter, stability of gap systems, disorder effects. The last is there because that's my main interest. Okay, so these are sort of some areas where there are mathematicians working, not necessarily at MSU. It's not meant to be inclusive of everything, but there are. Okay, and then my plan was to say a little bit about each of these areas. I think I maybe have too many slides, so I'll go through them a little bit. Maybe I don't need to explain this all to you. But I think I realized something about quantum information science. A few weeks ago, I had the pleasure of seeing Fernando Brandão give a series of talks at a conference I was at about quantum information science. And I sort of came to the realization that the big difference of quantum information theory is that within quantum mechanics, entanglement is a phenomena that we want to describe, and in quantum information theory or science, it's a resource that we want to. And I say it can be created, but that's not actually really true. It can be distilled, and that's the word they use, right? It's there, and we can try to extract it, and then we can try to use it. And so it's this perspective shift of turning entanglement into a resource that I think is what distinguishes quantum information theory from just quantum mechanics, and what distinguishes it from classical information theory. And I learned also from his talks that there were actually some surprisingly simple problems that are really as yet not understood. So he gave a very nice presentation about sort of bipartite communication, Alice and Bob, of course, communicating with each other with a quantum channel. But if you add Charlie to the equation, then there are problems that he could write down that it wasn't clear what the right definition of various quantities was. It wasn't clear whether the theorems go through. If you do define things, and this is something that I think is ripe for mathematical involvement there. So entanglement among three parties, essentially. Now, if you emphasize the quantum part of it, then this goes to the sort of a lot of the things I talked about on the second slide. Just questions about what types of systems can produce harnessable entanglement. How do we understand entanglement within realistic models or within cartoons of realistic models, such as lattice spin systems? Okay, and then finally the algorithm development. And I put this on here, so I'm sort of speaking partially for Matthew Hearn, who's in CMSE. I spoke to him yesterday about what he would have said if he were to be here. He was originally scheduled. And this is more in line with his interests. So, of course, we want to develop algorithms for classically hard problems, and this is what Leo has emphasized, is one thing we really need to be doing now so that we can hit the ground running when the scalable machines get here. Of course, this is hard, but there's another thing that you can do, which Matt mentioned to me in the conversation, which is just pick your favorite computational technique and ask, does it have a quantum analog? Okay, and he sort of jokingly said, right now you could write a paper for every classical quantum calculational technique. And I don't advocate that as a huge strategy, but on the other hand, such exercises are often a good way to get into something, right? As a good way to understand something. So, and then obviously people are interested in understanding quantum machines. Okay. So, and then let me just close by mentioning some of the activity here at MSU, since I'm the only one from math speaking right now. So I already mentioned Matthew Hearn. So his big interest is harmonic analysis and data science, and from the standpoint of, so this really should say not mathematical physics, but quantum mathematical physics, because I'm really emphasizing people who are interested in quantum mechanics and quantum phenomena. So his big interest is in machine learning applied to quantum chemistry. And he has a student, he told me, who's working on developing quantum machine learning algorithms, sort of adapting the machine learning algorithms that they're currently using. Myself, I work with a couple of students and postdocs on disorder effects in quantum systems, and we've started to talk some about quantum spin systems, and in particular the toric code that I mentioned, and some other simple models like that. Michael Shapiro is in the math department. He's not here. He has a long history of working with Mark Dickman. There's actually something else which should be mentioned here, because when Mark said this was done in collaboration with the math department, Misha was the collaboration. But his current real area of expertise is cluster algebras, which has nothing to do with quantum computing as far as I know, but it does have something to do with quantum physics, in particular quantum field theory, high energy quantum physics, and the computation of Feynman diagrams. And I think at the level that things are, it's probably not good to label boundaries between what's useful and what's not particularly strongly. If he's doing something that's related to quantum physics, then one should keep one's eye on it to understand whether it provides understanding of the quantum that you want to understand over here. And Lena Chekhov, who is a long-term visitor in the department, is an expert on random matrix theory and topological recursion, which has some relation then to the understanding of topological quantum field theories, and that relates back to the topological quantum computing. And then I've missed an entire group of people, as I mentioned, in the math department, which is perhaps our strongest resource, which is our geometry and topology group. Really, we have one of the better groups in the country on low-dimensional topology in terms of understanding some of the structure that goes into these topological quantum field theories. There are some people here who could be very good resources. And we have a couple of recent hires. Ilya Kakovsky is an analyst, mathematical physicist who's interested in quasi-periodic systems and some disorder effects in quantum mechanics. And Nelson is someone who we just hired who doesn't really do mathematical physics, but his interest is in a particular branch of functional analysis, which is instrumental in the understanding of the statistical mechanics of lattice systems, in particular of understanding and classifying phase transitions there, super selection sectors, and that kind of thing. So I see him as somewhat synergistic. And I just lastly want to mention the Institute for Mathematical and Theoretical Physics, which the OVP RGS was nice enough to fund for a number of years here. And we organized some seminar series and conferences. In particular, we've had conferences. I'm not listing the ones we have had. I want to point out ones that are coming here this summer. Phil already mentioned the workshop in the fall on quantum information science, but we have two interesting workshops in math physics coming up this summer, one in May, organized by Shapiro and a postdoc of his, and then this Great Lakes Mathematical Physics meeting, which is sort of broadly focused at people working within the field of mathematical physics. And actually, we always try to have at least one sort of quantum information person speaking at this meeting. Last year, it was Ramas Movasag, who I mentioned, who's at IBM, and this year it's Anna Vershanina, who's a professor at University of Houston and has done a lot of work on entanglement entropy with Elliott Lee at Princeton. So, and actually, that's all I have.